First things first, we're going to just revisit spectroscopy. So you did this in Nature of Light, and you should be very familiar with these three different types of spectra, and you should know how they're formed, and you should understand how they relate to each other. So at the very top, we have our continuous spectrum, and that's produced by a black body. And a black body is just an object that is a perfect emitter and absorber of light. So it reflects no light, it absorbs everything that comes its way, and then it emits a continuous spectrum of radiation. So all of the wavelengths. Now, it doesn't do those all evenly. Depending on its temperature, there'll be a peak emission wavelength. So if it's hotter, that peak wavelength will be in the shorter wavelength region, so the higher energy region. And if it's a cooler black body, it will be emitting that peak wavelength at a longer wavelength of radiation. And we'll have a look at that when we examine Wien's law again in a minute. The other two spectra you need to be aware of are absorption spectra. So these are the ones where we see the continuous spectrum with the black lines on top. And what I've given you here is a picture of Fraunhofer lines, and these were the first ones that were discovered, being like basically like these lines were first discovered by Joseph von Fraunhofer, and he saw these lines when he looked at sunlight, and he dispersed the light in a prism just like Isaac Newton had done with sunlight, but he could actually see these lines, which is really cool. And he saw a number of them, and now we realize there's a lot more because our technology's become much better. And you should basically remember from this that each of those lines is at a specific wavelength, and what's happening is you've got a continuous spectra passing through a cool gas. So in this case, it's the photosphere of the sun, which, I mean, let's face it, it's still very hot, but it's cool compared to the black body, and it's cool enough that those elements are going to be actually viable, and they're going to be there, and their electrons are going to be able to jump in their shells and absorb and release energy. So basically what you're seeing there is as that continuous spectra passes through that cool gas, that depending on what elements are in that gas, you'll get the absorption of particular wavelengths of energy, and those are considered like there's a signature for that particular element. So you can determine what the chemical composition of a star is by looking at those. The emission spectra are basically like a what's the word? Like a reverse image of that, I guess, a negative image of the absorption spectra. So basically, what you've got there is you've got an excited gas, and those excited particles are emitting energy with wavelengths that are equivalent to what they were absorbing in the absorption spectra. So, like the bright lines on an absorption spectra are at the same position as the black lines. Sorry, the bright lines on the emission spectra are at the same position as the black lines on the absorption spectra. And so they're the three, and you just need to remember how they're produced, and hopefully that's all okay. If not, go back to your Nature of Light slides and have a look at those, or go have a look at your textbook.